Okay, so we'll take it in English maybe? Right, it's recorded for YouTube?
It's recorded.
Yeah, cool. So I will present like a line of work that we have, which I call statistics powered ML. And here I will focus on specific situations where I want to obtain reliable inferences when I only have untrusted data. So how can we do so? And to motivate this project, imagine a medical application where we want to predict the true diagnosis of a patient given the brain MRI scan and some medical report. And imagine that we run our model, it could be even an API, and we get this prediction, like everything looks normal. And we look at this outcome and we immediately ask ourselves whether we can truly trust this prediction. And this concern stems from the black box nature of modern deep learning algorithms. Here it even could be even an API, right? So we don't really understand why the model makes prediction, or what would happen, how it would fail, how would look the test time failures, and so on. And in addition to that, we all know that we need high quality data, right, to train the model. In fact, not only to train it, but also to evaluate it. But having high quality label data is expensive, so we can find ourselves using some limited or low quality label data, or even synthetic data, both for training and evaluation. And of course, those problems make this question of building trust in ML inferences be very difficult to address. And so what I would ask myself here is, how can I obtain reliable inferences in such complex scenarios? And the approach I would take would essentially unify or integrate statistical testing and ML in a new way. And what I hope that I will be able to convince you is that this unlocks new opportunities to answer this difficult question. And so there are two parts for the talk. The main of the talk would be about part one, of how can we obtain reliable inferences in situations where we have really limited label data. And in the second part of the talk, which will be, I think, 10-20%, I would describe how statistical testing can actually be used to enhance robustness of models to test time drifting data. It's related to test time training or test time scaling, if you heard about this idea. So first I need to define what do you mean by reliability, right? Or each and every one here in the class probably has a different meaning for what does it mean to be reliable. So what I would try to argue that reliability for me is risk control. Okay, and I want to convince you why does that make sense. So in predictive inference tasks, right, like before, we have the input, we get some prediction. We don't know what is the risk, right? What is the error rate of this output? But if we would use a method called conformal prediction, the way you can think of conformal prediction is that it's a wrapper around any black box model. And in return of using this wrapper, you will get prediction set of possible labels. And what is nice about this set is that it is guaranteed that the unknown test label, the true diagnosis, will be covered in that set with high probability, say 95% probability. Okay? So what is the risk that I'm controlling here? The risk is the miscoverage error rate, defined as the probability that Y test is not covered in CX, in my prediction set, and I can control this at level alpha, which is user specified. Okay, so I'm controlling that risk. Now compare that to just having a naive prediction, right? We have much more information now. In the, yeah?
Can I ask?
Of course.
So if I get this correct, instead of giving a label as a prediction, you give a set, and then you're less accurate or less specific, but you minimize the risk.
Yeah, I'm reflecting my uncertainty, and my uncertainty controls the risk that I want. Yeah. And so the trick to achieve this is to use holdout label data representative of the test point, and then later I will say a few words about it, but that's, for now, that's what you should keep in mind. Yeah?
So what's the trade-off? Like, you can always do it by releasing also
Size of the set.
Yeah, so you're minimizing the expected size of the set?
No,
or
I'm controlling the risk, And if you have a bad model, or if there is a lot of uncertainty in your data, the sets will be large.
No, I'm asking just when you evaluate a method, well, you can always get
Yeah, yeah,
perfect zero risk by
Yeah, you
releasing all
show-
labels.
yes.
So what is your other
Set
measure?
size, or in fact something like conditional coverage. So it's slightly tricky, but for time being, let's say set size. Okay. So what we think about prediction, that this is everything in life, it's not, right? And there are other applications like statistical inference. That's a big deal, obviously. And think here about hypothesis testing, A/B testing. So just to have a concrete application in mind, imagine that I have some benchmark data and I want to conclude whether model A is better than B. And I can run some tests for the win rate. And a statistical test will give me a reliable outcome. In what sense? The decision will control the type 1 error rate, which is defined as the probability that I make a false conclusion, that one model is better than the other, although the two perform the same. And I will control this at level alpha. So here comparing models, it could be comparing drugs and so on and so forth. So the way I think about risk control is all about being honest about what I can truly infer from data at hand using the most sophisticated tools that exist out there. And one maybe nice application for that is close to my heart is that the Washington Post used the tools that we developed to reliably project the 2020 US election results with the Post readers. This is a joint work with people from Stanford, in particular with Emmanuel. And here, this is just a screenshot from the Post website. So that's the state of Pennsylvania, and the idea was instead of naively reporting who would win
They
this
removed
What?
Jeff Bezos removed the democracy dies in darkness.
Yeah,
This is an old logo.
yeah.
Now it died in broad
It
daylight.
died in broad daylight.
Yeah, but I like that logo, to be honest. And so the idea here was instead of naively reporting who would win the race, they actually reported those prediction intervals indicating that the blue is likely to win, but the red has some chance because there is some overlap between the two. And this tool was very successful. In fact, in the recent elections, it was used again. Of course, they improved the method, but you again see those prediction intervals. So the Post wanted to control the risk, okay? And so what is the general flow of what I've just described is that we have some representative data with risk controlling algorithm, and boom, we get reliable output. So it sounds terrific, but what's the catch? The catch is that we need that data, right? And sometimes it's really difficult to collect high quality and a lot of high quality data. Imagine that data collection is very expensive. Imagine that I want to analyze rare subpopulations, so I don't have much data, period. Or imagine that I just want to be very personalized. So think of model comparison. Instead of telling, hey, model A is better than B on the entire corpus of questions that I have, I want to be very specific. I want to test it on very small subset of math questions that I care about. Okay, I need that expertise. Or in uncertainty quantification, instead of being valid on average, I want to be valid for people like me of the same age group, the same, race, and so on and so forth. So the problem is that the more localized I am, the less representative data I have, right? I think that's clear. And once I don't have much data, I immediately face sample size barriers. So this can be reflected in low power. So right, if I give you 5 math questions and you want to evaluate models, there is no way you can make any reliable conclusion based on that. Or another issue is that you can have high variance in your conclusions, right? You will control the risk on average, but the empirical variance, right, will be low. So that's not good too. So you will get uninformative inferences in that case. Yeah.
Just to make sure that I understood the mechanism, what you're trying to predict is which subset of results have a higher chance.
No, so basically I told you you need representative data and you get a risk, right? So the risk will be controlled for that group of people, okay, of that group of questions, right? If you compare 2 models on math questions, it depends on a specific field. So the comparison, the outcome would be relevant to that particular field, that right subset of questions. So,
But how do you measure the risk? What is the risk control?
So it depends on the task. In conformal, the risk is the miscoverage, like what is the probability that I fail to cover the true label. In the case of hypothesis testing, is that I will make a false conclusion that model A is better than B, although the two perform the same. Okay. So what can we do? We don't have much data. Any ideas? Let's make it interactive a bit. You know, we live in 2025. You open Twitter, the first thing that you see is the word synthetic. Synthetic data, right? So,
It's the number one trending word on Twitter.
what?
It's the number one trending word on Twitter.
No, I don't know, but you see it a lot. LLM as a judge, let's say. Okay, so we all know that synthetic data is really useful, right? So most of the foundation models that we are familiar with partially trained on synthetic data, obviously. And in fact, synthetic data does not have to be only generative data, like from whatever diffusion model or LLMs. It could be also auxiliary data. It could be data coming from related subpopulations, related modalities, related sources. And today, of course, we have lots of diverse data sets. Think of domain adaptation, right? So that's a key idea there. But then the problem is that synthetic data is not the real data. It's not the trusted data. We cannot blindly trust it. It might be biased. There might be some distribution shift that we don't even know how to characterize. And in fact, Nature editorial wrote a very nice article about it, I think 2 months ago, in September 25. They say, you know, synthetic data is really beneficial, it could be beneficial, but hey, we must take into account the risk. We cannot blindly trust it. But then comes the question of, okay, so what can we do? Like, how can we use this synthetic data in a safe way and artificially increase our sample size if it's beneficial, but at the same time ensure the same safety standards of using trusted data? How can we do so? How can we break such sample size barriers? And so this is the first contribution that I will present, which we call General Synthetic Powered Inference, or GSP in short. So this reflects a line of work that we have. The first is synthetic powered predictive inference, focusing on conformal prediction, actually. So this is a paper that was just accepted to NeurIPS. And I came up with this idea, to be honest, like 2.5 years ago when I wrote my ERC grant. It's painful to write grants, but sometimes they force you to think long term. And I actually really much enjoyed working with the first project. And then we realized that we have something bigger in our hands, in fact. And this led to this recent paper that is actually a generalization of the first. The first is kind of a special case of the second, so I will present the second. This is a joint work with Meshi and Roy from my team at the Technion, and Yungun and Edgar from UPenn. Edgar is a faculty member at UPenn, and Yungun is doing his PhD there. And they're all really amazing. It's a really amazing team, and I'm grateful to have them. So what is this GSP? GSP is a general framework. It's a flexible framework. You can basically wrap or plug it into any risk controlling algorithm that you have in mind. It would automatically utilize synthetic data when it is beneficial, and at the same time it will give you formal error rate guarantees, formal risk control guardrail guarantees, no matter what is the quality of your synthetic data. Okay?
I'm trying to understand something. If you don't assume anything in the synthetic data, so the synthetic data is exactly like the samples you got not from the subpopulation you care about.
Few slides. Okay. And so the way I will explain this is, first I will try to give you some intuition through specific use cases, and then I will show you the general formulation and theory. Again, that's a general framework, so the general formulation theory might seem a little bit abstract, so I want to build the intuition first. Okay. So let's start with predictive inference. So how conformal works? I have some holdout label data. I compute the prediction error of my model on this holdout data, and then using those prediction errors, I found some threshold over the estimated class probabilities, and all the class probabilities that pass the threshold are included in my prediction set. Okay, so now here my set contains label 1 and 2. And this method essentially gives you this guarantee that the miscoverage is bounded by alpha, and this guarantee holds as long as the holdout and test points are IID or in fact exchangeable. So this is one, actually, the only assumption of conformal is this IID assumption. Another thing that I want you to notice is that if I increase the risk level from alpha to alpha plus epsilon, from 5 to 10%, say, then what can happen is that I can reduce the size of my set. I can take more risk. I can ignore some class labels. That seems to be likely. And the third thing that I want you to notice is that this is a tight guarantee, right? In the sense that if you give me large n, the miscoverage will essentially be alpha, almost equal to alpha. It shrinks as 1 over n. And so we like large n because we get tight guarantee, and not only because of that, also because the set size, the number of samples, can also affect the set size. So what do I mean by that? Like if you give me very small n and you ask for small alpha, small n and small risk, the only thing that actually I could do is to give you the trivial sets that contains all the class labels. Right? If you give me 10 points and you ask for a 2% miscoverage, there is nothing I can do. Okay? And later we will see that. Yeah?
So I think that we need to assume that our data is independent of each other, because otherwise we can just generate more data points from the data we got, and they will be dependent.
You needed a test point will have the same distribution of your holdout data. So if you generate data, the test point may not necessarily come from the same distribution. Right? The test point is the truth. The synthetic data is, fuzzy. Okay. So we want large n. So we like big n. So what can we do? Well, again, we use this synthetic data. These are samples coming from some distribution Q. The real data comes from distribution P, and so is, of course, the test point. And we're crossing fingers that the synthetic data is close to the real. After all, LLMs are generating great text, or diffusion models generate nice-looking images, but we don't really know, right, that they're coming from the same distribution. And so, and we again want to use it to break the sample size vary. So, how does JSP work? So we take this a risk controlling algorithm. In our example, this is conformal prediction, and we run it 3 times. Once what we call synthetic powered, second guardrail, and third base. So we get 3 outputs. We will somehow aggregate them together in a very special way that will give us the reliable output that we're interested in. So what is this synthetic powered? Synthetic powered is a case where this is the most naive thing that you can think in mind. We take the real data, synthetic data, pull them together, and just run conformal at level alpha. Okay? So if the synthetic data is of high quality, if P equals Q, then it is just running conformal on a huge sample size, and that's great. We have our big N. But what if we have low quality synthetic data? Well, we are in trouble because synthetic and because the holdout data that we have in test points are not ID anymore. So no guarantees. So to gain robustness, we must hold tight the truth in a way. So how can we do so? We are going to run conformal twice on the real data, only on the real data. Once is what we call the worst case guardrail. So what does it mean? You're going to run conformal at level alpha plus epsilon, not alpha, alpha plus epsilon, higher risk, higher level of risk. And the way you can think of this epsilon is the admission cost. How much risk you're willing to pay if in the worst case you have bad synthetic data. Okay, you control this epsilon, and that's what you should have in mind about how to set this epsilon for now. Okay, so that's the worst case guardrail. And the third thing is just running the base method, the classic conformal algorithm at level alpha on the real data, as if there is no synthetic, no nothing. Okay? So now the question is, how can I aggregate the 3 prediction set, and what is the meaning of this, the aggregated outcome? So how to aggregate? So first I will take the red set, in that case that's just the normal label, and I will compare the union between the red and the synthetic powered set, the blue set. Why union? Because I want to make sure the risk at the end will be alpha plus epsilon in the worst case. So what does it mean? It means that I have to include at least all the red labels, right? It doesn't make sense to ignore them. But then I don't want alpha plus epsilon risk. I dream for alpha risk. So what can I do? Just augment to them the blue class labels. In that case, I will augment to normal the concussion label. Okay, the intuition here is that if P equals Q, I actually reduce the risk from alpha plus epsilon in the worst case to alpha. If the data is really bad, I will have alpha plus epsilon in the worst case. Okay? And that, so again, you can think of this epsilon as a parameter that controls the trade-off between how much risk I'm willing to take versus how much I would gain from using synthetic data. Okay? Yeah.
Just to make sure I understand, you hope that the synthetic powered gives you the same set sizes as the guardrail, and then
No.
some.
I hope that the synthetic power give me exactly sets with risk alpha. That's my dream. But I don't know that. So what I do, I take the guardrail, which usually constructs smaller sets, and then I'll augment to them the sets from the synthetic power. So I will reduce the error from alpha plus epsilon to alpha if I have good synthetic data.
But the sizes of the sets themselves, you hope
Will
to
increase.
be-
Yeah, I want them to increase because the guardrail is too small. Okay? It controls a more liberal risk level. Yeah.
What exactly is the guardrail?
Run conformal prediction, run your risk controlling algorithm at level alpha plus epsilon instead of alpha. So instead of controlling the risk at level 5%, ask the method to control the risk at level 10%.
Okay. With this example, with normal, concussion, and cancer, like, why is guardrail normal, base with three of them, and synthetic power is
Because here you can take more risk, so the set is small. Okay, here you want alpha risk, and let's say that synthetic data is perfect, so you get actually the set that you want. And this set is large because you don't have much samples. So with small n, you have more uncertainty.
And the goal is that the correct outcome will be inside the set?
Yeah.
Or that,
Yeah.
That is
Yeah. Okay, and so and lastly, what I do, I take the intersection between between this couple and the base method. Why intersection? Because I want to make sure that no matter what, I will never perform worse than the classic algorithm in terms of set size. Okay, so you can only benefit in terms of set size if you use that method. Okay, so let me show you how does it work. So here I took this ImageNet data. I want to cover the label 95% of the time. I want to do it conditional for each and every class. So it's kind of personalized for each class.
For each class or
For each
image?
class. For each class.
Okay.
So for example, if I have Husky dog, I want to make sure that the label Husky is covered 95% of the time. And of course, at that time, I don't know that that's an image of a Husky. And so I have 15 real data points, label points from ImageNet. Of course, this is nothing. So what I do, I use Flux to generate 1,000 points per class. Okay. This is a subset of ImageNet that contains 30 class labels, just because people were angry about us where we just use all the GPUs to generate lots of synthetic images. So it's a subset of ImageNet, but this is really doesn't matter anything.
Why does that bicycle have two?
Yeah, we can. Yeah. Yeah, there are lots of
It's a real
issues.
bicycle?
Yeah.
Tandem, I think it's called.
No, but what? I don't think this would.
Yeah, I don't know why they like the. Yeah. So. Yeah. So what you can see here on the left is coverage, and the right is the set size. The dashed line is the level that we want, 95. So the triangle, the green triangle, is the outcome of only synthetic, of only real, sorry. So that's basically the classic conformal method that I run only on the real data. You can see that the coverage is 100%. So I'm controlling the risk, right? It's above 95, like the 95% coverage. And on the right hand side, you can see the size, and the size is 30. 30 means it just produced trivial sets because n is too small. So now what I do, I run conformal prediction only on the synthetic data. You know, what can go wrong? Like Flux is so great, is a great generative model, right? So you can, first you can see that we get smaller sets, which is great, but the problem is that there are some class labels like ASCII where the coverage is 60%. Okay, not 95 as we wanted. And the third thing is JSP. This is the blue method. And first you can see that we achieve the safety standards. This is what I promised you. And we also get smaller sets. Now, I want you to notice two things. First, just by looking at synthetic data, it's really hard to tell if it's good or bad, to be honest. So this is like images generated of ASCII. They look terrific, but they're really bad for the purpose of quantifying uncertainty of my clip model. Okay, so that's somewhat surprising maybe. And another thing that I want you to notice is that if my synthetic data is good in the view of the statistical task that I want to solve, then the JSP method benefits from it automatically, right? You see the variance of this box plot is shrinking and I hit the alpha, the 1 minus alpha coverage. Yeah.
What is our metric when we take a look on the test sets size, on the set size? I see that on the plot on the right we prefer smaller sets, but how do we measure if some algorithm performs better than another? Because otherwise it's always good to choose the whole set.
No, so I want small sets and I want valid coverage.
Yeah, so
Yeah, so
what
these are
I'm
the
trying
two
to ask
metrics.
is how do we measure what a small set is? How good the performance of small sets do?
So yeah, that's a great question, to be honest. So first, if you have two algorithms, and the one that gives you the smaller sets, and where both control the coverage, that I think indicates that one is better than the other. But actually, the answer is more subtle than that, and I would love to discuss this maybe offline because you hit a very, very important point, actually. Another thing that I want to show you is that JSP is not the worst case guardrail. Okay, it can actually correct it when the synthetic data is good. So here what you see in red, this is the conformal that I run at level alpha plus epsilon, right? That's our guardrail algorithm. And now what you can see is that when the synthetic data is bad, if garbage in, then the JSP and the guardrail are just the same because synthetic data is not useful. But when the synthetic data is useful, then you see that the blue has smaller variance than the red, right? So actually enjoying the higher quality of the synthetic data and producing more informative outcome than just having the guardrail method. I want to stress this point of the guardrail bound. Okay, so it turns out, and later I will show you the theory, is that the guardrail bound holds no matter what is the quality of the synthetic data. Okay, period. No matter what is the quality. So in fact, it can hold even if the synthetic data and real data are dependent. Okay, and that's a tricky thing. But it's very powerful. Why it's so powerful? Because imagine that I give you, 15 data points. And now I ask you, okay, give me synthetic data. What can I do? I have to look at them. Right? I will look at the real data points, and I will generate my synthetic data. I will filter out samples that look bad. Maybe I will change the prompt to generate better images. Or maybe I will just decide how to collect those synthetic data to start with. And I can do all of that without worrying of double dipping, without worrying of overfitting. I will have this alpha plus epsilon guarantee in the worst case. Okay, so let me show you a scientific application that I hope will convince you why this thing is so useful. So here my goal is to basically give you the sequence of residuals to predict the 3D structure of a protein. And I will do it using AlphaFold, and we all know that AlphaFold is great in the sense that the predictions are fairly accurate, corresponds to, now he's shipping, never mind. They correspond to the real structure, and of course they won the Nobel Prize for that. It's amazing now we can predict 3D structure of lots of protein that we don't have the structure because it's really expensive to collect. But the fact that they won the Nobel Prize does not mean that they never make mistakes, right? So we want to highlight the local regions in the in the predicted structure that the error is, let's say, larger than 3 angstrom. And we can do so using a method that is called conformal risk control. It's a sister method, kind of conformal prediction. I will not dive into all the details, but the point that I want to say is that now we can control a different risk. The risk here is the average fraction of residues who has this large prediction error. I want to control that at level alpha. Okay, so that's what I want to do. And the way I can work with this data, of course, to run this method, I have to have test and holdout data. And the benchmark data set that I will use is CASP14. Okay, that's kind of the ImageNet of protein 3D structure. And what is so nice in that data set is that we have the real experimental structure, but of course it's very limited. It's extremely expensive to collect this structure. So what can we do? Or in other words, how can we create a synthetic version of CASP14? What does it even mean? Okay, and here is a nice idea that Meshi had. So there is a very interesting component in AlphaFold which is called MSA. So the way you can think of MSA is like a nearest neighbor, very smart nearest neighbor algorithm. So given X, it basically sweeps over terabyte scale databases and find nearest neighbors, kind of nearest protein structure, amino acid sequences that are close to that X. You can think of this as RAG for proteins, okay? And this MSA is very important in AlphaFold to improve the prediction error, actually to improve the prediction quality. And the idea that we had was actually to use MSA, those nearest neighbors, to obtain synthetic data. So I find it really cool because it's like AlphaFold bootstraps itself, not only to obtain more accurate predictions, but also to ensure the reliability better. Okay, so that's this idea behind those MSAs. And so these are the synthetic data that we have. And obviously the synthetic data is a function of the real data, right? We look at the real data, so they're dependent. And what you can see here, that JSP controls the risk as promised. And you can also see that the abstention rate is smaller than the one of the classic method. So let me show you it visually. Maybe you would be convinced that it's actually useful. So on the left you can see the outcome of conformal risk control, the classic method, where we have really small labeled holdout set. So we want in general to have lots of blue regions, because blue means, okay, that's a prediction that we can trust, but we want the blue regions to actually reflect the truth, right? We want to mark a region in blue when it's actually close to the real structure. So what I do here, I just blend together in gray the true experimental structure on top of the predicted one. And now you can see that in the regions that I marked them in red, on the right and both on the left, there are actually mistakes. These are the unstructured regions. But when there is structure, actually AlphaFold does a great job when you mark that in blue. Okay. So thus far we discussed prediction tasks. And of course, again, prediction is not everything in life.
So in general, you're not improving the prediction, right? In JSP. You're just giving better coverage.
Yeah, I give you better risk control in a way, yeah.
And how are you using, I understood you have these 3 groups, the guardrail, and if there's a difference and you know something is wrong, but if you know that something is not wrong, why do you get a better risk?
What I get a better.
What allows you to get a better?
So it's not a better risk, like
higher coverage, I guess.
No, so the thing is that, like, if you run the base method, right, at level alpha, you will control the risk at level alpha.
Yes.
And also you will do the same with JSP.
But you have a big.
Yeah, but then there are 2 things that can happen. Either that you will have high coverage variance, or you will be just very conservative. conservative means that instead of 95, you will give me 100% coverage. Okay, so by adding those extra points, you can either shrink the variance or, yeah, okay, cool.
So, just to make sure, from practical perspective, you clearly showed how it's useful. From the theoretical perspective,
Wait few slides.
oh, there's going to be.
Yeah, it's great.
I was
Your
waiting. I
questions
thought
are
the few
excellent
slides already
questions.
came.
Yeah. So let me focus on the most basic statistical inference task, hypothesis testing. I have a parameter theta, and my null is that theta equals theta naught, and the alternative theta is larger than theta naught. For example, think of model comparison where theta is the win rate, right? Theta win rate means that model A is correct and B is incorrect, and I want to test whether theta equals 1/2, the two models perform the same, or model A is better than B, win rate greater than 1/2. Okay, and so I can run a statistical test for that. In fact, it's basically a binomial test. And the outcome of the test will be either 0 or 1. 1 means, hey, yes, you can reject the null and conclude that A is better than B. Okay, that we have evidence for that. And if phi equals 0, it means I don't have enough evidence. Okay, I cannot reject the null. And this algorithm phi controls the type 1 error rate. Okay, that's my statistical test. So I control the false rejection at level alpha. And so how would you apply JSP in that case? Again, you apply the same algorithm 3 times, once on the pool data at level alpha, once on the real data at level alpha plus epsilon, once on the real data at level alpha, and then you need to combine. You notice that the combination, the aggregation is different, and let's read the aggregation together carefully. So when you reject the null, you can reject the null if the base algorithm rejects the null, okay, only on the real data at level alpha. If that rejects, done. There's no point to continue anything. But if it does not reject, I still have the opportunity to increase power and still say that model A is better than B. How? I have that to make sure that both the synthetic powered and the guardrail agree with each other, that both reject. Okay, so if both of them reject, I can also reject. Okay? So let me show you one example for that. So here I want to tune a hyperparameter of reasoning model on math tasks. My hyperparameter would be k in majority vote. So we know that if we increase the k in majority vote, we expect the accuracy to improve, let's say, up to a point. And so, but this comes of course at the cost of computational complexity. So I want to compare expensive k, 64, to cheaper choices of k, like 1, 4, and so on. And I'm going to test this on M25, that's my real data set. I'm sure that you heard about it if you work on reasoning models. It's a small data of 30 fairly tough questions. And the synthetic data, auxiliary data here would be this Olympiad bench. It's a larger, it's a subset for me, it actually containing 630 questions. And here what you can see is the rejection rate for different configurations of this hyperparameter. I'm comparing two different choices. And what you can see is that first, the choosing K64 seems actually to be better than 1 in terms of performance, right? And this should not surprise us. You can also see that JSP has higher rejection rate than the classic method, so that's nice, we improve power. At the same time, you can see that 64 is not really better than 16. Why? The rejection rate is around the error level that I want, right? Alpha. And so we don't have actually evidence to say that 64 is better than 16, so you just basically maybe wasting your compute. And there are lots of other applications for JSP. We applied for mechanistic interpretability, and the test is two-sample testing. We applied for outlier detection or out-of-distribution detection. Synthetic data is noisy label data. We applied even to multiple hypothesis testing, for example, to control the family-wise error rate, and so on and so forth. And the JSP has also always this general formula. You run the base risk control algorithm 3 times and then you aggregate. So finally, to your question, let's understand the theoretical foundation of this method. So in the set of base states, I have real data samples from P, synthetic data samples from Q, and I assume that I have a risk controlling algorithm ALG. Okay, that's my base algorithm. So the way that ALG works is that I get input, Z, the input space, and the output is what I call the action space, okay? So in conformal prediction, right, the input are X, Y, the algorithm is the one that constructs the C hat, right, the prediction set, and the action space are the prediction sets themselves that I'm constructing, right? In hypothesis testing, the input is the data, the algorithm is phi, and the action space is 0 or 1, except reject. Okay? What I assume about this algorithm, I assume that it controls the risk under distribution P. So the expected value of some loss of the algorithm is bounded by alpha. Okay? What is the loss? Depends on the task. In conformal prediction, the loss is the miscoverage rate. In hypothesis testing, the loss is false rejection, right? The false indicator, the false rejection indicator. V is the evaluation variable. It could be a test point, it could be nothing, depends on the application. And I assume that the risk is controlled at level alpha for finite and for any distribution P that belongs to this calligraphic family of P. All the algorithms that I showed you thus far are actually achieving this. In conformal, the calligraphic P are all the distributions under X, Y. It's a distribution-free algorithm. In the case of hypothesis testing, these calligraphic P are all the null distributions. Okay, so we have the algorithm, and now we want to apply JSP, right? So to do so, intuitively, we need to understand how to aggregate actions that obtain once on the synthetic data and once on the real data. And to aggregate actions, we need to understand which action is better and what does it even mean to be better. So here is a condition that we require, which is a mild condition that in fact holds for all the applications that I discussed thus far. So the condition states the following. Given two actions, A1 and A2 from the action space, I want to be able to compare these two actions. What does it mean? I want to be able to say, to define some partial ordering. I want to say that A1 is smaller or equal than A2. I want to understand this relation between the two. And I also, in a second, I will give you concrete examples. I know that maybe it's a bit abstract. And I want that or I have to have, that the min and max operators are well defined. The second thing that I want is that once I know how to compare, I want to choose the better action. Better action means lower loss, smaller loss. So if A1 is smaller than A2, I want the loss of A1 to be smaller than A2. Okay, that's my condition. It's really mild, and let me convince you that this is the case for example, hypothesis testing. So my two actions here are don't reject, reject. Okay? They happen to be ordered by the smaller equal operator that we are familiar with, and the minimum and maximum are well defined. These are the AND and OR operations. If you remember a few slides ago that we discussed this, we had this AND OR in the aggregation. It's coming from there. And of course, the loss is monotone, right, with respect to A. If I don't reject, the loss is smaller than the loss of making the rejection. Right? So if I don't reject, I don't make mistakes. Okay. Under this construction, we now can understand how to design the aggregation scheme. And what is the idea? The idea is that we take the action obtained by the worst case guardrail, we take the action obtained by the synthetic powered method, and we compute the mean between the two. The mean action. Why mean? Because we want to clip the risk at level alpha plus epsilon in the worst case. This is why we take the mean. And then finally we take the max with alg alpha. Why? Because we want to make sure that we are not more conservative than the base method, level alpha. Okay. So that's the idea. Here in the table you can see what is the partial ordering and so on. We saw that before. I hope that you have the intuition at this point. So let me show you the theoretical result. One is for a simpler version of JSP. We call it one-sided guardrail. we just take the mean between the red and blue. We don't have the base, the green method. And what this theorem states is that as long as the condition holds and the algorithm, the base algorithm controls the risk, then the risk of GSP is bounded by alpha plus mean between epsilon, the admission cost, and dpq. What is this dpq? Is some discrepancy, in fact it's a TV distance, between the loss of the synthetic algorithm, synthetic part algorithm, and the real algorithm. Okay, the algorithm that works on synthetic data and with the discrepancy between these two loss functions. And so notice that this is a distribution-free guarantee, and don't make any assumptions on P, it could be anything. If P equals Q, if I have perfect synthetic data, TV distance is 0, and boom, the risk is alpha. But if the synthetic data is really bad, or depend on the real data, it doesn't matter. If TV distance is infinity, say, then the risk will be alpha plus epsilon, no matter what. Okay. What about the two-sided guardrail? That's the algorithm that I showed you throughout the talk. So now I have the max with alpha alpha. So one result that we have is the action of just P always falls between the base and the guardrail. So what does it mean? In simple words, it means that you will never perform worse than the base method, the classic method, but your performance is capped by the worst case guardrail. Okay, so this is why I told you before that epsilon plays this trade-off between risk and power. Yeah.
Usually, which one of them is closer to the green one or to the red?
Well, it depends on so many things. Yeah, it's a general result. So, but I can explain you if you want. I can discuss this offline and show you specific cases what happens. We also have a result for the two-sided guardrail for risk control. Actually, it could be tight up to some bias, but I think I will skip over this because I see that I'm running out of time. Is this correct? Yeah. So I will skip over this, and I will just conclude maybe this part by showing you at least my takeaway from this work. So Samuel Wilks is one of the fathers of distribution-free inference, and in a beautiful paper from 1941, he asked this question, like, how many samples do I need to collect in order to construct a stable prediction interval for a quality characteristic of a product? Okay, here it's a diameter of a washer, shaiba. Okay, imagine an industry. Okay, and the answer, of course, was an analytical expression, but so roughly speaking, you need 1,000 samples for that. And fast forward to 2025, the point of GESP is to tell you that if you happen to have high quality synthetic data, you can actually break this barrier, okay, and benefit from synthetic data to construct stable prediction intervals. I don't know if I have time for the 10 minutes. Oh, 10 minutes is a lot. Okay, so I will quickly present this work, which is about using sequential testing to enhance robustness of ML models. It's
Related to the previous one?
no, except the word statistics is part of it. Yeah, it's just the general idea of having statistics powered ML. Okay, so it's a joint work with Yarin and Shalev. All right. So we all know that ML models perform great if they're applied on in-distribution data, but once the environments are changing, bad things can happen. Here you can see the accuracy of vision transformer model trained on ImageNet over time. And over time, we just changed the test set. Started with the original ImageNet test set and then changed the illumination, contrast a bit, and you can see accuracy drops. And this is really annoying because, you know, the shift is not that severe. I just change the illumination and still it drastically affects performance. And so ideally we want to enhance the robustness of the model to these shifting environments. But this is tough. This is challenging because first we don't have up-to-date labeled samples at this time, in the extreme case. And second, we don't really know what would be the test environment that we get, right? We might have gradual shift, we might have sudden shift. it's a different setup from classic domain adaptation that you know the target distribution and now you have the time to prepare to it. Now, you run on the fly and things are happening. And so there is an emerging idea which is called test time training. It's related to test time scaling, if you heard about, and I would say it's basically transductive learning. And the idea is the following: so you have some pre-trained classifier. Here, vision transformer model I downloaded from Hugging Face. And then at this time, what I do, I take this green F and I keep training it on my test data. Of course, I don't have labels, so I'm minimizing some self-supervised loss. The way I can think of this loss is some regularization of how I believe that the model should act at test time. Okay, I want to basically bake these beliefs in the model at test time. And of course, this is a big question of which self-supervised loss should I use even, and would that work well? So if you're familiar with entropy minimization, that's one popular choice for self-supervised loss. So what I will show you in that talk is essentially a new training paradigm for test time training that is motivated by two key questions. The first is, how can I alert you? How can I basically monitor the behavior of the model, and what does it mean even behavior of the model? And then the second is that if I can detect that the model behaves differently, so why not correcting it? Why not changing the behavior to the way that I want it to behave? And it builds on, again, ideas from sequential statistical testing. So what is the problem setup? I have some source domain. These are the usual image data that we are familiar with. The target domains are those red X's. And the way you can think of this red axis is that I first sample a green X and then I apply some transformation to it, Tj. The transformation is unknown, it can vary over time. Imagine transformation like changing illumination, contrast, whatever. Of course, I have to make some assumptions about Tj because if you just blank the image, there is nothing I can do. So the assumption that I would make is that the condition distributions are the same under the source and target domain, okay, defined by this transformation Tj. It's a very common assumption in domain adaptation or in causal inference related to invariant predictions, if you're familiar with this. In simple words, what it means that the prediction difficulty is not changing because of T. Okay, the problem not becoming harder or easier. The reason that you see performance drop is because the model is not prepared to that environment. Or more concretely, what this is telling you is that imagine that I have my oracle classifier trained on the source domain, and I look at the vector of class probabilities for the XS that I fed, and now I have another oracle model trained on this red domain under Tj, and I again feed the same XS to the new model. The vector of class probabilities should be the same. Okay, that's, or must be the same, that's the assumption. And so based on that assumption, we basically came up with our proposal, which surprisingly, I don't know how no one thought about it before, because it's again a very common assumption, and our proposal is essentially to update the red F, the model F on the fly, so that the distribution of the outputs of the red F will look like the distribution of the outputs of the green F evaluated on in-distribution data. So in simple words, what we want to do is online distribution match between the test environment that is keep changing and the source environment. Okay, so that's what I want to do. But it's tough, to be honest. And it's tough because if you think of this, the red axes are keep changing over time. And not only that, F itself is changing over time because I keep training it. So I have kind of highly nonlinear stochastic process, and I want to match this distribution to that distribution for time steps. How can I do so? Yeah.
To clarify that I understood, you mean that if I'm given a test sample, I run Tj on it, and I want to try to...
No, just wait a second, you will see. Okay, sorry for that because we have 2 to 3 minutes. Okay, so now I have a stream of X's. Okay, that's my test data. I will show you a method in high level. In fact, under some assumption, we actually achieve this matching. But of course, we need strong assumptions for that. So we have this stream data. and we feed the output of the model to a drift detection tool, which essentially alerts you when the output of f is diverging from the green distribution, roughly speaking. And then I take this outcome of the drift detection and I feed it to anti-drift adaptation that essentially tells me how to update the parameters of the model such that the drift detection tool will not be able to detect drifts anymore. It might remind you GANs or adversarial training. It's related to it. It's great that you have this intuition, but it's completely different. In a second you will see why. So let's dive into the drift detection. That's where statistics, the first part, the statistics kicks in. So the game is this: I get to see a red output and I want to test whether it looks like green outputs. Green outputs are outputs that I computed on my holdout data on in distribution with the green F. So how can I test that online? Okay, so the way I can do it though is using testing by betting or conformal martingales. I don't know if you heard about it. It's a pretty cool idea. So essentially you run a casino now, okay, and you give me $1, and my goal is to bet against the null, bet against, so you give me red X, and I'm basically betting toy money on how much I believe that the red axis that I see is different from the green axis, okay? If I win the bet, my wealth will increase. If I lose the bet, the wealth will decrease. I will not explain how to form the game, not that it's that difficult, because you just don't have time, but I can form a game, okay, that is fair, in the sense that I construct a martingale. So what does it mean? It means that if there is no shift whatsoever, there is no way on earth that you will make money. You will make profit on average, okay? So no shift, the profit on average should be 1. But if there is a shift and you know how to gamble well, your profit can go up like crazy. Okay, so that's the drift detection tool. And then what I do in the next step is I have this anti-drift adaptation, and the idea is to fool the gambler. The idea is I'm going to tell you how to change the parameters of your model such that the gambler will not be able to make profits anymore if they use the same betting strategy. And we have an analytic formula for that. It's not adversarial training. The effect of that, it's essentially a loss function that you minimize. The effect of this is distribution matching. If you have the ideal betting function, if you're kind of the king of the casino, and the ideal betting function here is the likelihood ratio, and in fact it's related, or it's in fact an online optimal transport. Actually, that's what's happening behind the scenes. So I think I'm running out of time. You had great questions. So I'll skip over this. To cut a long story short, it works great, and we have state-of-the-art results. Otherwise, I guess the paper would not be accepted. And to sum up, we all know with the famous saying, all models are wrong, but some of them are useful. Right? I'm sure you heard about it. So in light of this talk, I would add all data sources are imperfect, but some of them are still useful. And I hope that I convince you that this is actually the case. So thank you so much for being with me for the last hour. Thanks. Yeah.
In the first part of the lecture, when you give a set of predictions, I wanted to ask if, don't we prefer to give probabilities for each classification to let the user know which one of the results were more...
Yeah, of course, that's a dream. But the problem is that you don't know the probabilities, right? So in regression, if you think, if I would have in my training data the probabilities, I could regress them, and then I could construct prediction intervals for them.
But I can construct probability vectors such that label is 1 and the other is 0?
Yeah, this is true, but then like the inherent, the challenge is that how can I know that my probability is actually close to the true probability of that X? So you don't know them, but it's related to other works on calibration. There are other notions of calibration. Probably you heard about those reliability plots that P hat should be close to B for a given that you make a prediction. And so there is a different notion of calibration, kind of probability calibration that is relevant to what you said, in fact. Yeah, but it's a bit tricky to construct a set of for probabilities because I don't see them. Okay, sure.